Welcome back to another video. Today we're going to summarize the beginning of reaction mechanisms in organic chemistry. So the first skill we're going to learn how to do is how to classify halides. So if we have a halide, which is a halogen, on a regular carbon, just like that, that's called an alkyl halide. So number 3 over here is called an alkyl halide. Now if we're connected to a carbon, but that carbon has a double bond on it, that is called a vinyl halide. And then if we're just connected to a benzene ring, that makes us a benzylic or aromatic. Now also another thing about classifying halides is whether it's primary, secondary, or tertiary. So if we have this carbon right here and it's connected to 1 and 2 more carbons, that makes it a secondary carbon. And if this one's also connected to 1 and 2 more, that makes it also secondary. And this one's connected to 1 and 2. All 3 of these are secondary halides. Now, we also have to know how to name these halides. So it's pretty similar to how we used to name everything else. All we do is just add the bromo for bromine and chloro for chlorine, fluoro for fluorine, just those prefixes. And we just have to number them. So we have this cyclobutane over here, and we have a bromine and a chlorine, and they seem to be cis because they're on the same side. So all we have to do is just figure out which one is carbon number 1. So we're going to go with the bigger halogen, so bromine. We're going to make this chlorine. Also, bromine is alphabetically before chlorine, so that's another reason to make it rank number 1. So we're just going to have it 1 bromo, and then 2 chloro. Alright, and then it's just going to be cyclobutane. And we also have to write cis. So before that, we have to write there cis because it's on the same side. Now, another thing we have to do is compare dipole moments. So if we're comparing dipole moments, what are we doing? Well, we have to look at the actual molecule. We have a cis 1,2-dichlorocyclobutane. So imagine this, but we had 2 chlorines versus a trans where one's going up, one's going down. Now, we don't even have to draw it because polarity has to do with the direction of the dipole. So if we have one chlorine pointing upwards and another one pointing downwards, the dipoles are going in opposite directions, so they're going to add up to 0. But if we have 2 pointing in the same direction, then they're going to add up to a larger net dipole. So we're going to say that our cis is our more polar molecule, while our trans is our less polar. So there's the first 3 skills. Now, the next few skills is how to compare the boiling points. So if we have 1 bromobutane versus 1 chlorobutane, well, we know that bromine is larger than chlorine in size. And so, if we have larger in size, we have more surface area. So if we have more surface area, we have more London dispersion forces, and that increases our boiling point. So the boiling point of this one is larger than this one. So that's the first thing we have to do. Now, the other skill we have to do is know how to do allylic bromination. Now, allylic bromination is pretty neat. What we have is 2 bromines attached to each other, Br2, and you add UV light to it. So what ends up happening is that the electrons over here, they homolytically cleave, which means that they split evenly. So you end up getting a bromine radical. Now the first propagation step is that you have this bromine radical and it attacks some sort of carbon group that has whatever other groups it has. And this radical is going to attack this hydrogen. And so the hydrogen is also going to take 1 electron with it. What we end up getting is HBr and some sort of carbon with a radical. Now, what makes something allylic is if this entire process happened, but with a carbon with a double bond. So if we had this group instead, the bromine is going to attack the allylic carbon. Now an allylic carbon is one that's right next to a carbon with a double bond. Not the one with the double bond, but right next to it. So what's going to happen is this bromine radical is going to attack the hydrogen. Hydrogen is going to take one electron with it, and we end up getting this product. So we have carbon, double bond carbon, another carbon, and we have the radical right there. Now we're just going to ignore these extra groups that these carbons have. So what can happen here is resonance stabilization. So we can actually stabilize this through something called an allylic shift. And what we end up getting is this structure right here. So I forgot to draw one more substituent on this. So we end up getting this structure right here. We have the two groups, and then we have our radical. So this is an allylic shift. It's when the radical moves to not the next carbon, but the one after that, when our double bond or a pi bond moves over to create resonance. Now, does the whole pi bond move? No, actually. We only have one electron move. So you have one electron move, the other one moves, and we actually use half arrows for this. And you form a pi bond here, and then you just have a radical left on this carbon. And then the second propagation step is just the same thing, where you have one of either product with the radical, and this just attacks a regular bromine. So if you have bromine over here, Br2, what it really is just two bromines attached to each other, and we're going to have the same process happen again, where the radical is going to attack one of the bromines, and then one of the bromines is going to take back one of its electrons, and you just end up getting this product right here, and then you have your bromine bond. Now you either get this or the product when it attacks this molecule right here. So you can actually end up getting up to 2 products total. So that's allylic bromination, where you have an allylic carbon, it forms a radical, and then it's resonance stabilized, and so you end up getting up to 2 products. Now, another thing we have to consider is how to classify substitution and elimination reactions. So finally, we're actually going to get to the core of reactions. So with substitution reactions, what it is that you have a nucleophile, some sort of reactant. It might have a negative charge, it might have a lone pair, and it's going to replace the position of a leaving group. So we're going to start defining these pretty soon. So a leaving group is just the group that leaves, and then we have our nucleophile is the reactant that attacks. And when it forms a substitution, what ends up happening is that this reactant just takes the place of the leaving group. So over here, this methoxide right here just took the place of the bromine, and the bromine just ended up bonding with the sodium that was originally on the methoxide. So this is called a substitution. Now, elimination, elimination reactants, we're not going to go into in too much detail today. However, what it is just getting rid of the leaving group without adding a new group to it. So over here, this OH ended up somehow leaving and getting some sort of positive charge on it, and we had a double bond here. So this is called an elimination reaction, where you get rid of the leaving group. Now, what is the reaction mechanism for this? One of the things we have to consider is that, one, we have something called a backside attack. So this nucleophile, whatever it is, it has a negative charge, it has a lone pair. This lone pair is going to attack from the backside of this carbon, and then what's going to happen after that is that this leaving group is going to take this lone pair with it and try to leave. So we end up getting is this transition state that's slightly negatively charged, where we have our nucleophile connected to our carbon, which has its 3 groups again, and then it also has its halogen / leaving group. So these bonds are actually not completely formed yet, so they're partial bonds right here. So these are partial bonds, and we end up getting in the final product is that we have our nucleophile right here attached to our carbon, and then our halogen usually leaves. So we end up getting plus this leaving group that's usually negatively charged. So that's the reaction mechanism of SN2. Some things to notice, that SN2 stands for second order reaction. What does that mean? If you look at the rate constant for this reaction is dependent on the concentration of two things: concentration of the nucleophile and the concentration of the substrate. Both of these affect the reactivity of this reaction directly. So if we double the concentration of the nucleophile, it doubles the speed of the reaction. And same thing with the substrate. So it's a concerted reaction. It happens all at once. There's no intermediates in SN2 reactions. We simply will get a transition state and instantly our product. So it's pretty fast. Now, we're going to practice a little bit on this SN2 mechanism. So if we have this propane that has an iodine on it, and then we have the sodium cyanide, how is it going to work? Well, we have our iodine, and we have a negatively charged cyanide. Now the negative charge is on this carbon. So what's going to end up happening is that this carbon, or this cyanide, is going to attack from the back side of this carbon, and this iodine is going to take the lone pair with it and leave. So we end up getting this product right here. So we have our propane, but now our new group is the sodium or the cyanide group. So this group right here, don't forget this lone pair, plus the iodine that's just chilling on the side with a negative charge. Now, this next example right here, we don't know what the nucleophile is, but we know that somehow we replace this chlorine with this OH group. So what could this group be? Well, one group that we could suggest that it could be is NaOH, sodium hydroxide. Sodium hydroxide has a negative charge. It has 3 lone pairs that we can't see right here, and it's a strong nucleophile. So what could have happened is that this sodium hydroxide, the hydroxide part, attacks the carbon from the back, and then chlorine just takes its lone pair with it and leaves, and then the hydroxide group now replaces that chlorine. So that's some basic SN2 mechanisms. Now, trends in nucleophilicity. How do we know if something is a strong nucleophile or a weak nucleophile? Well, here are some of its trends. If you have something that's less electronegative, it's going to be a stronger nucleophile. So compare an oxygen to a nitrogen. Nitrogen is less electronegative, so it's going to be a better nucleophile. Now, if you have a negative charge, that makes it even better. So an oxygen with a negative charge is slightly better than an amine that has no negative charge. And then an amine with a negative charge is better than an oxygen with a negative charge. So same trend in electronegativity and then negative charge. Now, one more thing that makes nucleophilicity better is the size. If you have a bigger atom, it's more polarizable. So what that means is that its electron cloud is bigger and it can be more easily stretched. See, when you're trying to form the bond in this backside attack, your electron cloud is going to stretch a little bit in order to attach to the carbon. So if you're larger, you're going to be more polarizable, and it's going to be easier to form SN2 reactions. So you're going to be a better nucleophile. So this is better than that. Now, what about this last group right here? Well, the thing with that is that we have our OH just like this one. However, we have 3 methyl groups on the side. So if you remember what steric hindrance is that you have extra electron clouds on the sides that interfere with a reaction. So if this nucleophile is trying to attack from the back side of any substrate, these methyl groups can get in the way of actually doing that. So this makes it the worst out of all these that we just ranked because of that steric hindrance. So steric hindrance does have an effect on your nucleophile. Now, another thing we have to consider is the solvent effects. So if you have a regular SN2 reaction, here we have potassium fluoride, and we have a polar aprotic solvent with 18 crown 6. So just as a fun fact, 18 crown 6 simply ionizes fluorine, to make it a better nucleophile. And then here we have the same thing, but instead we have methanol, which is a polar protic solvent. So if you're polar and aprotic, means you have no hydrogens that can form hydrogen bonds or that are acidic, you're actually going to get faster reactions for SN2. Why? well, think about polar protic solvents being like the paparazzi. Acidic protons are going to get in the way of the nucleophile. So this is actually going to be slower. Now, another thing we can consider is the leaving group. Now, how do we know if leaving groups are better? Well, if your electron withdrawing means increased electronegativity, you're going to be a better leaving group. Why is that? Because you can polarize the carbon you're attached to, aka you can form a partial positive on the carbon that is going to be attacked by the nucleophile, which is attracted to positive charges, and you can more easily handle negative charge. Now, what about a chlorine versus hydroxide? What makes this a better leaving group? Well, you have to be stable when you have a negative charge, like over here. When this leaves, we're going to get chlorine with a negative charge versus a hydroxide with negative charge. Which one is more stable? Well, hydroxide is a strong base. What does a strong base mean? It means it's very reactive. So if you're very reactive, you're not going to be stable versus a chlorine, which is pretty stable with a negative charge. So the stability of the conjugate with a negative charge is important. Now, what about chlorine versus iodine? What's the difference? Well, iodine is down the periodic table, so it's larger. And if it's larger, it's more polarizable, and it's also more stable with a negative charge because its negative charge is more spread out through its electron cloud. So this is going to be better. So just to reiterate, you have to be able to be electron withdrawing, you have to be stable as a negative charge, and you have to be larger. So let's compare. Now, another thing you have to consider is the leaving group versus the nucleophile. When can it work and when can it not? So bromine is a good leaving group, and sodium hydroxide is a strong nucleophile. So you can get this to turn into this. You can have the hydroxide attack from the back carbon, and then bromine leaves. But what if we had the opposite? What if we had hydroxide over here and bromine acting as a nucleophile? Can it work? Well, hydroxide as a leaving group is terrible because, like we said over here, hydroxide is extremely unstable as a negative charge, while bromine is pretty stable as a negative charge. So this cannot happen. Now, there's a special example over here. Well, we have the same scenario as this, except that instead of its sodium bromide, it's HBr. It's hydrobromic acid. So what could this actually happen? How could this actually happen? Well, if we have our hydroxide group and HBr, that means we have an acidic proton and negatively charged bromine. Well, this acidic proton, we have lone pairs on this oxygen, and they can actually attack this acidic proton. So we end up getting is this group right here, OH2, so it has a positive charge, and we still have our bromine, so bromine with a negative charge, right? So now this group is a water group. It's two hydrogens and an oxygen. That's a really good leaving group. So what's going to end up happening is that this group is going to leave. It's simply just going to take this lone pair with it, and bromine is going to use its negative charge and its lone pairs to attack this carbon, and you're going to end up having a product that looks like this. So you can't actually get this to work. So if you have an acidic proton with a bromine, you can't actually get this to work. Now, what about some steric effects on the substrate? So like we said, there is steric hindrance with the nucleophile, but what about the substrate? Well, if you have a nucleophile attack from this back carbon, if it's simply hydrogens, they're really small electron clouds. They're not that big now compared to a methyl. So you can get, it's possible to get a result. So you'll just get the hydrogen there, your methyl there, and then your other hydrogen there, and you simply have your oxygen with its carbon. Now, what about this right here? Well, it's almost impossible to get a product from this because this carbon right here is tertiary. It has 1, 2, 3 methyl groups attached to it. So if this methoxide tried to attack from the back, it almost can't reach that carbon. It's pretty much impossible for it. So steric hindrance can play a big role on SN2 reaction speed. Now, one of the last things we're going to talk about is the inversion of configuration. So we already slightly showed this, but we didn't talk about it. So if a nucleophile attacks from this backside on this carbon, and like we said, we get this little transition state where the carbon has slight bonds and we have this shape right here. What ends up happening is that the nucleophile is over here, but now the carbon, as we look at its bonds, it inverted. So what do we mean by that? Well, the halogen, say this was R, say this molecule was R and it was chiral, this nucleophile, after attacking, could actually turn this molecule into S if it were to work out that way. What I'm saying is that these bonds simply just switch out. It's like an umbrella. If this was an umbrella pointing this way, now it's pointing this other way over here. So that's what inversion configuration does in SN2 reactions. And that's actually called the Walden inversion. So what does that also mean about SN2 reactions? That means it's also stereospecific. What does that mean? If you have a carbon and it's chiral, your product is also probably chiral as long as the nucleophile doesn't become a second group on that carbon that's equivalent to an already previous group. So if you're going to be given a problem and it has a chiral carbon, you better show the chirality on the product. So here's an example. If you have 2R bromopentane, so let's draw that out. If we have 2R bromopentane, so we have a pentane group, and it's R bromine, so that's actually this reactant right here, or substrate. And you have potassium cyanide. What's going to end up happening is that you have your lone pair on the carbon is going to attack this molecule, this carbon, from the backside, and so your final product will look something like this. Since this is attacking from the backside, wouldn't it just make sense to say that the stereochemistry is like this? It makes perfect sense, because if the bromine is in the front, this nucleophile is going to attack from the back. So that's what your final product is going to look like. So that's all there is to SN2 reactions. I hope you enjoyed today's video.